So I'm going to go ahead and outline a general procedure that'll take care of all of our transformations, no matter how many of them we have in any type of combination. All right, in order to use this standard procedure, we're going to have to think of our transformed function in a standard form. So if g is a transformation of some starting function f, then we're going to want to think of writing g using function notation as a times our function f evaluated at b times the quantity x plus c plus d. So an important note is if we want to use this procedure I'm describing, we have to write the inside of our function in this factored form. So the inside of the function has to be in this factored form, otherwise we're going to misidentify one of our transformations. All right, so we've seen all these transformations individually and know individually what they do to our function, and that is still the same. We just have to be careful about how we put them all together. Before we talk about how to put them all together and the order we're going to use for our transformations, let's go ahead and quickly review what each of these parameters, a, b, c, and d, do to our function, what type of transformation they cause, and how we actually perform that transformation. So here we have a, which is the factor the outside of our function is being multiplied by, right? We won't maybe always write our function in this function notation and identify a, b, c, and d, but we do need to be able to identify an outside factor, an inside factor, an inside term, and an outside term in order to perform these transformations using this general procedure. So a is our outside factor, and we know that that is going to correspond to a vertical stretch, compression, or flip of our original function f. And the way we perform a vertical stretch, compression, or flip is just by taking the original y values from points on the graph of f and multiplying them by that number a. We call a our stretch or compression factor, and if a is negative, we also have a flip in the mix as well. All right, so up next, just working from left to right, is our parameter b. b is our factor inside of our function. So if the inside of our function is being multiplied by b, we know that that's going to correspond to a vertical stretch, compression, or flip of the graph of f, depending on the value of b itself. So if b is a large number, multiplying by a large number actually causes a horizontal compression, and if b is a small number, between 0 and 1 in absolute value is what we mean by a small number, then multiplying x by a small number is actually going to cause a horizontal stretch to the graph of our original function f. So the way we actually perform these stretches, compressions, and flips horizontally is we take those original x values from points on the graph of f and we multiply them by 1 over b, or divide them by b. That number 1 over b is our horizontal stretch or compression factor. Remember, these horizontal transformations kind of work opposite or counterintuitive of how you would expect them. So instead of multiplying by b, we divide by b, and that's why we had that weird little rule. If b is large, dividing by b or multiplying by 1 over b causes everything to shrink. And if b is small, between 0 and 1, then multiplying by the reciprocal of b, or 1 over b, or dividing by b, is actually going to make everything much, much bigger. So our last two transformations correspond to addition or subtraction, depending on the value of c and d. C is our addition or subtraction happening inside of our function. That's going to affect x values and therefore be a horizontal shift. Remember, it's a horizontal transformation, so it's kind of counterintuitive. We don't add c to our x values. We always subtract that number c from our x values. And that last one, that plus d, kind of looks like the same color here, but it's supposed to be more yellow. That's going to be a vertical shift. When we have addition or subtraction happening outside of our function, that's going to affect our y values. We just add that d value to all those original y values from the graph of f. So one important note that I want to reiterate is if we want to use this general form and read off our transformations from this list here, we have this requirement that the inside of our function has to be factored. Otherwise, if we didn't have this factored, it look like bx plus b times c, we would misidentify that horizontal shift. But another important note when working with transformations of function is that the order matters. The order is so important when it comes to these transformations of functions. It is possible to do the order of transformations in a slightly different order than what I'm going to describe, but if we're using this general setup and procedure, we're going to have to use it in the order I describe. And the order is actually going to be pretty counterintuitive. We're always going to do all of our stretches, compressions, and flips all together at once. And then once we performed all these stretches, compressions, and flips that are occurring, only then do we take care of the shifts. With our setup, we need to do it in this order because if we do our shifts first and then stretch or compress, we end up actually stretching or compressing those shifts we just did, which then changes how much we shifted by. So our order matters. We're always doing our stretches, compressions, and flips first, followed by our shifts. And an easy way to remember this is just remember the order of operations, right? In the order of operations, we always do multiplication and division before addition and subtraction. If we think about our transformations, well, our stretches, compressions, and flips correspond to multiplication, either inside or outside of our function, and our shifts correspond to addition or subtraction. So we do all of our multiplication first, all of our stretches, compressions, and flips first, and then we do all of our addition and subtraction, then we do all of our shifting. All right, so we've talked about the general procedure that we can use for graphing combinations of transformations of functions. Now let's go ahead and take a look at an example of putting this procedure into practice. So in this example, we want to graph g of x, which is equal to -2 times the absolute value of the quantity x minus 3 with 4 added on at the end. And so just by looking at the equation and the fact that there's an absolute value quantity involved and no other weird functions showing up, we can identify that this is in fact a transformation of our absolute value function. So let's go ahead and let f of x just be our starting function. Of course, that's the absolute value function. And next up, what I want to do is express our equation for g of x using function notation like we have over here for our general procedure. This step may not always be necessary, but it's nice. It helps you show your work, and it helps you identify what the inner and outer factors and terms are when trying to identify these transformations. So let's see. The absolute value is our actual function itself. This -2 is a factor outside of the absolute value. So it's happening outside of our function f. Normally we just have x inside of our absolute value function, but now we have x minus 3 inside of our absolute values. So our input is not just x, but it's x minus 3. We also have this plus 4 we have to take care of that is outside of our absolute value brackets. So that plus 4 is happening outside of our function. So very quickly, we rewrote our function in this general function notation, not necessarily a required step, but it does now allow us to quickly identify these parameters a, b, c, and d, and what type of transformations are occurring. So we have this -2 out front. That is our a value, and that corresponds to a vertical stretch by a factor of 2, as well as a vertical flip. So we're going to take some of the key points on the original graph of f of x equals the absolute value of x and perform this transformation by multiplying all those y values by -2. So I'm not going to keep up with the color coordination here, but our next parameter is b. That's the number that x is being multiplied by, and we should factor that out if necessary, but that's not necessary here. We do not have an obvious b value, so b is equal to 1, and nothing really happens, right? We can almost just ignore the fact that b is equal to 1. That doesn't really correspond to a stretch, compression, or flip, so we're just multiplying x by 1 over 1. It doesn't change anything. You don't even actually need to write that if you don't want to. All right, do we have a c value or parameter? It looks like we do. c is equal to -3. And so remember, this is going to be a horizontal shift, but it's always kind of counterintuitive. Subtracting 3 from x inside the function intuitively makes you think you're shifting to the left 3, but it's actually the opposite. We're going to the right 3. We're going to add 3 to all those original x values. The last piece we have to work with is that +4. That's like our parameter d in our general form, and that corresponds to a vertical shift up 4 units. All right, so here I have the graph of our original untransformed absolute value function and about 5 of those key points identified. What we're going to do is perform our transformation to just these 5 key points, track what happens to those points, and then replot them after all the transformations have occurred. That should keep the overall shape of our function and let us see what the new version looks like. All right, so here's a way that I recommend kind of showing your work as we perform all these transformations. I'm going to make a table. In the first column of my table are going to be the key points from the starting function or the untransformed function. So these are just going to be points on f of x, and the 5 points we decided to use, or I decided to use, were -2, 2, -1, 1, 0, 0, 1, 1, and 2, 2. So now in the next column of my table, I'm going to perform our first set of transformations to our starting function and its key points. And remember, our first set of transformations are all the vertical stretches, compressions, and flips. So we just have a vertical flip and a stretch by a factor of 2 happening here. So we'll just perform that transformation in this column. And then in the next column, we'll take care of our second set of transformations, all the shifts. The idea is intermixing the stretches, compressions, and flips is not going to matter because a horizontal stretch is not going to cause anything to change vertically, and vice versa. A vertical stretch, compression, or flip is not going to cause anything to change horizontally. So what we're really actually going to be looking at in our second column is not f of x, but a vertical flipped and stretched version of f of x. That's going to be -2 f of x. All right, so in this first set of transformations, we just have a vertical transformation, so all of our x coordinates will not be affected, right? Our x coordinates are only affected by horizontal transformations. Our vertical transformations are only affecting these original y coordinates, and what's happening to them is they're being stretched by a factor of 2 and flipped. We're just multiplying our y coordinates all by -2. So our original +2 up here gets multiplied by -2, turns it into a -4. We multiply that original 1 by a -2, it becomes a -2. 0 remains 0. And our last 2 points, y values, become -2 and -4 respectively. So we've taken care of our stretches, compressions, and flips. The only transformations left over are our shifts. And here we have 2 shifts. We have a shift to the right 3. So we're going to have to add 3 to all of our x values. And we also have a shift up 4. We're going to have to add 4 to all of our y values. And so once we perform these transformations, we will then be looking at -2 times f of x minus 3 plus 4, better known as g of x to us. So we've already taken care of the -2 out front. Already multiplied our y coordinates by -2. Now we're adding 3 to all of our x coordinates. And I usually like to do all the x values together and then all the y values. But you can do it point by point. You just got to keep everything straight. So if I add 3 to all of these x values, I get 1, 2, 3, 4, and 5. Then remember for the y values, we're shifting up 4, so we have to add 4 to all these y values from our previous column. That'll give us 0, +2, 4, +2, and 0. So now with these 5 transformed points, we can plot them and sketch a graph of our transformation g of x. And so here I have plotted those 5 points, connected the dots, staying true to the original shape of our function, just that kind of flying V shape. And we can see that we have the transformation that we expected. Right, so if we take our absolute value function in orange over here, stretch it vertically by a factor of 2, flip it over, shift it to the right 3 and up 4, we end up with our green graph over here, or our function g of x. And so the overall procedure that we used here was we looked at the equation that was given to us, we identified the transformations that occurred, we then identified some key points or features on our graph, transformed those points corresponding to the transformations we identified, plotted the transformed points, connected the dots, and sketched our graph.